Lecture 23. Basic properties of dividers and couplers. Now, this will be the application part for the course. We're going to investigate the microwave devices and also the circuits, both passive and active. Okay, so applications for microwave would include, first is the divider or combiner, a transmitter receiver signal to or from many antennas. Okay, that is one application. And then you have separating forward and reverse propagating wave, can also use for sort of matching. And you may also have a signal combining for a mixer. Okay, those are three examples of microwave devices application. So we're going to look into a two-way power splitter and power combiner. Okay, now power splitter would have the form as in the first figure here. So power splitter is when you have P1 coming over the divider or a coupler and then provide P2 and P3. So that's why we call it as power splitter. It is split into two. So this is a three-port network because you have P1, P2 and P3. Okay, the same device can also be used as a power combiner where you have two power and then you combine it. So you have P2 and P3 going into the divider or the coupler. Okay, so here the case would be a coupler. So you will have P1 is equal to the addition of P2 and also P3. Okay, so here it is also a three-port because you have P1, P2 and P3. So we can see that even the simplest divider and combiner circuits are three-port network. Okay, so it is common to see dividers and also couplers that will have more ports than that. So it should be three-port and more. Okay, three or more. Right, the basic properties of a three-port network. Okay, we are going to show you that it is not possible, I repeat, not possible to construct a three-port network that would have all these three requirements: lossless, reciprocal, and match at all the ports. So this is the basic property of a three-port limits our expectation for power splitter and also combiner. So we have to be loosen up a little bit in a way to design it. Okay, so to begin, a three-port network has an S matrix of the form like this. Okay, remember, because it is three-port network, so your S matrix will be 3 by 3. So that's why this equation. Okay, now if the network is matched at every port, okay, what does it mean by match? So match is when your S11, S22 and S33 is equal to 0. Okay, it is important to understand that match at every port means that your reflection coefficient at 1, 2 and 3 will be equal to 0 when all other ports are terminated in Z0, because it is three-port network. That's why you have up until S33 only. Okay, now if the network is reciprocal, your S21 will be equal to S12, S31 will be equal to S13, and your S32 will be equal to S23. Okay, so consequently, for a match and reciprocal three-port, your S matrix would be like this. So why do you have this equation? Because S11, this is S11, S11, S22 and S33 is matched. That's why it is 0. Now reciprocal meaning that your S12 would be equal to S21. So that's why you have S12 over here instead of S21. and then S13 would be equal to S31, okay, and your S23, sorry, here S23 would be equal to S32. Okay. Note there are only 3 different S parameters in this matrix, which is S12, S13, and S23. Finally, the third requirement, it should be lossless. So, when you have a lossless network, your S matrix should be unitary. Okay, what does it mean by unitary? We have learned in the previous lecture. So, unitary is when the magnitude of S12 squared plus S13 squared is equal to 1. Magnitude of S12 squared plus S23 squared will be equal to 1. And your magnitude of S13 squared plus magnitude of S23 squared is equal to 1. So by applying all those equations, you will have the conjugate of S13 times S23 is equal to 0. Conjugate of S23 times S12 is equal to 0. And the conjugate of S12 times S13 is equal to 0. Okay. Now, it can be summarized that at least 2 of the 3 S parameters must be equal to 0. So, if this is the case, then not all of the equation is satisfied. Because, say, if you have S13 is equal to 0, then 6 and 8 are satisfied. But, for 7 to be satisfied, where your S23 should not be equal to 0, we must have S12 is equal to 0. Okay, but with S12 and S13 both 0, then 3 cannot be satisfied. You see, so the 3-port network cannot be all 3. It cannot meet all the 3 requirements, which is lossless, reciprocal, and match at all ports. Okay, that's why you have to loosen a little bit in order to design the 3-port network. Okay, so however, one can realize such a network, which is the 3-port network, if any of these 3 constraints is loosened a little bit. Okay, you shouldn't be too strict. So here are the 3 possibilities. The first one is you make it a non-reciprocal 3-port instead of reciprocal. So in this case, a lossless 3-port that is matched at all ports can be realized. It is called a circulator. So a circulator would be a non-reciprocal 3-port, okay, where your Sij is not equal to Sji. Next, should be match only 2-port instead of 3-port, okay, match only at 2, alright, assume port 1 and 2 are matched. So here we assume as port 1 and port 2, meaning that your S11 and your S22 is equal to 0 because it is matched. So S11 0, S22 0. But at S33 it cannot be 0. And finally you have lossy network. So meaning that all ports can be simultaneously matched and the network is reciprocal. Next, we have the 4-port network. So, unlike 3-port network, 4-port network is possible to make it lossless, matched, and reciprocal. So, we can satisfy all the 3 requirements. So, we call the 4-port network as directional coupler. So, the S matrix of a reciprocal and matched 4-port has the form of equation 7.9. Because it is 4-port network, that's why your S matrix is 4 by 4. Okay, what does it mean by match? Meaning that your S11, S22, S33 and S44 is equal to 0. Reciprocal meaning that your S12 is equal to S21, S13 is equal to S31, S14 would be equal to S41, S23 would be equal to S32, S24 would be equal to S42, S34 will be equal to S43. Now, incorporating the fact that the network is lossless puts further constraint on these S parameters. Okay. Now, there are two commonly used realization of the directional coupler. So, the first one is the symmetrical coupler, and the second one is a symmetrical coupler, not symmetric. Okay, the first one, the symmetrical, meaning that you have the S matrix for this device as equation 7.17. So if you see the S matrix, you can see that it is symmetrical. Meaning that here, if you slash over here, you can have alpha, alpha. So your S12 will be equal to S21. Your S13 will be equal to S31 and so on. Okay. So it is obvious from this matrix that the network is reciprocal and matched. It can also be shown that the S matrix is unitary, which is also mean that it is lossless. Next one, the asymmetrical coupler. So the S matrix for this device is shown in the equation 7.18. So you can see here that it is not symmetrical. Why? Because if you slash over here, beta, you have here beta, but here is minus beta. Okay. In the previous one, when you have JB over here, you have J beta. So here you also have J beta. Okay. So we can see from this S matrix that the network is matched and reciprocal. It can also be shown that the network is lossless. Alright, now take a quick look at the operation of a directional coupler. So the circuit symbols are shown here in the figure, these two figures over here. So these arrows, okay, you see, these arrows over here indicates the assumed direction of the time average power flow. So the S matrix for the symmetrical and anti-symmetrical directional coupler, okay, would be like this, where the dash here indicates a non-zero value, okay. So this would be the coupling for the directional coupler. So C will be equal to minus 20 log 10 of the magnitude of beta in dB. The directivity would be D is equal to 20 log 10 of the magnitude beta over the magnitude of S14. Isolation would be I, represented by I, which will be equal to minus 20 log 10 of the magnitude of S14. And finally, the insertion loss L will be equal to minus 20 log 10, the magnitude of alpha in dB.